Hello everyone, spiral matrix for August the 7th. You start at the cell R start, C start of a row times column grid facing east. A northwest corner is at the first row and column in the grid, and the southeast is at the last. You will walk in a clockwise spiral shape to visit every position in the grid. Whenever you move outside the grid's boundary, we continue our walk outside the grid, but may return to the grid boundary later. Eventually, we reach all of them. Return the array of coordinates representing the positions of the grid in the order you visit. So give a start position, in his case here, and then the first move is always to, it's clockwise. So the first move always to the right, and then down to here, to here. Okay. So in this one, start at 1, 4, 0, 1, 0, 1, 2, 3, 4. So first is go here, 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 here. We'll go out, coming down here, visit everything, go out. And we want to return an array of coordinates representing the positions. Holy crap. Okay, it's an array. It's all right. So, all right, so we have a starting position, right? So we definitely go to the right as much as we can, right? Once we hit the end, we go, no, not as much as we can. I think we only go out once. We only go out once every time. We go once, down once, count to the left, go up. So I can, let's say, get the position, the starting position, and the direction. So we have 4 directions, right? And then in that direction, we need to move. But how many times we shall move? Well, technically we don't know unless if we keep counts. The first one you move once. First down, move once. First left, it's not move once. You essentially you're here, you move twice. Then you move twice. Then you move 3 times. So I would say every 2 changes you have to increment the number of moves, right? Well, you can prove that because whichever direction you move like n times, and then you move n times down, right? Because you already covered n times going right, so now you're going left, you have to do 1 more. So it doesn't matter whichever direction. You do 2 directions. Now actually it does matter because the only 2 directions that have the same number of counts is right and down, right? Right and down always have the same count. Left and up always have the same count. So right and down, now you got a +1. Left and up, now you got a +1. Right and down, +1. Left and up, +1. You just keep doing this, right? Keep doing this, okay? So we go left, we'll go right and down, right? We just keep counting. So if we go 0, 1, 2, so 0, we go 1, right? And a 1, we'll go down, we count as 1, and then now we go left, right? When we go left, we have the previous. Now we go previous +1. The 2 times. And then So 0, 1 is the same. 2, 3 is the same. So every time you hit a divisible by 2, an even count of turns, you will increment by 1. If it's odd, it don't change. Okay, that's fine. Totally fine. And then we have the positions. That's fine as well. So we have positions. So now we know starting from which position you need to go how many times. Right? Okay. So you know which position you start, and you know the direction, and you know how many times you need to go, so you can compute the next one. But the goal is to list out every single one. So you just have to go through every single one. But there's a catch, right? There's a catch. The catch is we don't want to list the ones that's out of bounds, right? Which we can avoid. Like in this case, we are ending up at, so we're at this position, and we know to go to the right 3 times because that's the 0, right? You're going to go to 3 times. So we do 3 times, and if it's more than what we need, we just skip, right? We just skip. And then we know we're going to go down 3 times. So we go down 3 times, and because it's skipped, we can set its, okay, I think we can do this. I think we can do this. Have a general idea of how I wanted to solve this, and then we just need to see if it will work. So the way it works will be directions. I mean, technically, directions. Directions. It's fine. Int directions, new int. So we're gonna say go right will be 0, 1. Go down will be 1, 0. Go left is 0, minus 1. And then go up is minus 1, 0. Okay. So that's the directions, right? And then we have our starting position, and we need to know int steps. Okay. Now I know the total numbers, right? So we can say int res equal to new int. Actually, we know this. This is 2, and this is going to be rows times columns, right? And int I equal to 0. Okay, so while I is smaller than rows times columns, right? So we get it, we move it to the next position. Let's call it index, because I also need to have I equal to 0, no, I equal to R start, J equal to C start, column start and row start, right? So every time we do this, we are at whatever we are, and then we're gonna move forward. Right, so we need to first say how many turns, right? We need turns. So steps, turns. Right. So 0's turn, we can say if turns mod 2 is equal to 0, then steps plus plus. Okay. Now we need to move the number of steps based on the current turn, right? We move the number of steps based on the current turn. And every time we do it, we push more, because initially I think the start has to be inside. Okay, so the index has to start with 1. Okay, because I say res 0 shall equal to new int r start c start. Okay, so now index is where we're supposed to be, and we just call for int k equal to 0, k smaller than steps, k plus plus, right? Then what we do is we say res index shall equal to new int. Well, we do this first. I plus equal to directions turns, right? Directions turns 0. J plus equal to directions turns 1. If I is large equal to 0, now if I is smaller than 0, or I is larger equal to rows, or j is smaller than 0, or j is larger equal to columns, then we will break this. Right? Otherwise, this will equal to new int ij, right? And then after you do that, index or plus plus, right? Index or plus plus. So we find the turn, right? We find the turn, and then we increment this. We put this into the result. Then we go for the next step. We do this until one of them get out, okay? Or we finish the turns, right? We finish the turns. Now we'll get out, okay? So this turn is over. So turn shall equal to turn plus 1, not 4. So, right? And then we need to figure out where the I and j is right now. Now it depends on if they are out of bound, right? If they're out of bound, then there's nothing we can do. If they're not, yeah, so basically because we're incrementing, or maybe decrementing, right? So if they're outside, so we need to pull it back in. Because the last one will be the correct one, then we go for the next one and then go out of bound, right? And then we go for the next one, right? The next one we will have, something will get inside. Okay, that's actually not truly correct, because if I go out of bound, let's say I is correct, but j go out of bound, right? Now we need to go down, right? Now we need to go down. So what we need to do is first check if I and j is out of bound. If I or j, like say if j is out of bound, right? And then we're going up or we're going down, that we basically can skip this, right? We can skip this round and then go to, holy crap, depending on how many steps we need to go, right? Depending on how many steps we need to go, because in this case, I want to go back in, because here we go 1, 2, 3, right? And then go, and this one, we know the steps, so I know I can do 1, 2, 3. I get to this row, but column wise, I have to set it to this position. But I do 1, 2, 3. It should be actually 4, right? 1, 2, 3, 4. Should be actually 4, because this shall actually go here, right? So it goes in. So basically, I will compute where it should be, right? Okay. It will be easier if we don't have to go through all the extra complexity. We just iterate through them, like all of them, even if those are not what's required. But I always try to see if it's possible without, and we can compute the next position. But the question is, then you need to have a new one to compute, right? The position is really not based on you, right? It's not based on you. That's the problem, right? That's the problem. I mean, we can. Yeah, because it can get really complex. I mean, you can skip some, right? You can skip some, but at the end of the day, if you skip some, then you need to have extra count of steps and stuff. You can't just use one step, right? Because you need to know how many steps need to be skipped, so you know. Maybe we can do that. Yeah, we have steps, which is the overall step, right? And before we go through, we will compute what the actual number of steps that need to go through. So we go here, right now we have ij, right? So ij will pointing to ij is the starting position. So we'll have actual ij, the overall ij and the actual ij. So we can try to skip, right? So we can call them ti, tj, and ts, t steps, right? The temporary, current. So steps gets updated. We have ij as the actual position, which can be out of bound. Now we need to compute the actual steps and actual start position. Right, the actual steps and actual start positions. So we have the step. I know ij is the imaginary position. Then what I need to know is, based on the current steps in this direction, okay, how many do I need to move, right? How many times do I need to move? So if it's within the boundary, right? If ing is within the boundary or someone is outside the boundary, then I need to compute the final position, okay? I can, based on where I start and where I end, and I have the final position. All right, I have the final position and the ing. I think I can do that. I have the final position as long as it goes inside. Well, would it be possible that as we go out, and then we go out, and we go, actually it's not possible, because once we like go all the way out, then we don't have any more left, right? If you go spiral, and at the end, right, if you go out, the only case where you go out that it doesn't come back in is you're already out. So as long as you have something inside, it will always loop back in, right? You will always loop back in. Okay. So we'll see how many. Okay, so we'll say and I shall equal to I plus directions turns 0 times steps and j plus directions turns 1 times steps, right? So I calculate the end ij. So we start from ij, going to end ij. I just need to know I just need to know how many within this is inside, right? How many within this is inside. So I do, well, it depends, because I basically go through all of them, right? We'll go through all of them. Yeah, I can say from from this to this. Oh, also depends on So we are going from, yeah, we can list I and then go through I and go through J. I and JJ, right? So I will be starting from I I guess it depends. If I is larger than, then we need to start from here. If I is smaller than, then we need to start from here. So we need to get a maximum of these two. It depends, right? If I is out towards the right, then we need to get a minimum. And then we'll get, so we get a minimum first. Minimum between this, the maximum between this. So we get a starting I position. And we have an ending is the same. Okay, so we can get a starting position and an end position. And then we go that. And then we have that. Then we put that into the consideration. Okay. This feels like an easier way to do it, right? So we have to say for int I is equal to math dot minimum I rows minus 1. Right, we'll get a minimum of the 2. And then we need to get a maximum of the 2. Maximum of 0 and this. Right? So if I is out of bound, then the minimum will get to rows minus 1 and the maximum will go to rows minus 1. Right? And if it's not out of bound, so it's within, then the minimum will get there, maximum will get there. Right? If it's a negative value, then the minimum will get there, maximum will get, yeah, I think this is, so I larger or equal to 0 and I smaller than rows and I plus equal to directions turns. All right, so int di equals to directions turns 0, int dj is equal to directions turns 1. Okay, then we can move this to di, this to dj. Okay, and we'll move this to di as well. Okay, and then for int j math.max, essentially the same thing, 0 math.min j, and then there's a columns minus 1. And j smaller than columns, j plus equal to dj. Okay, then what? Then we fill in the blanks. We say result index plus plus equal to new int I, j, and j. Right. So we go through them. Then why you compute the ni and nj? What's the purpose of computing them? Yeah, that is the trouble. So I need a little function here. Otherwise, yeah, I guess it's fine. All right, what we're gonna do is we'll copy this. Oh, is it larger or equal to or smaller or equal to? Good question. It depends on the direction. If di is larger than 0, then we're going down, right? Then we need to smaller or equal to and I. Okay, so basically, oh my goodness. N, I, and J. Si. Oh, I see what you're trying to do. So we can do that. Right, this is Si, Ei, and I rows minus 1. Sj. So this will be columns. Right, this is J into Ej. Should be Nj. Right. So I have a start I, Ni, start J, and J. So now we can say start I. Now this need to change. Basically, di is larger than 0, and ii shall be smaller or equal to ei and I, right? Or di is smaller than 0, and ii is larger or equal to ei. We can put 0, like put 0 here, right? If it's larger or equal to 0, then it has to be smaller or equal to, yeah? If it's smaller, then we're going up, it has to be larger than. Okay, so now we need to copy this and put it here. And of course, everything's going to change. This is going to be dj, and this is j and j. This is going to be ej. This is start j, right? If it's start j, and then we do this. So now we fill out everything. Now once we fill out everything, we need to do the next thing is we have ni and j, right? So well, we just need to say I is equal to ni, j is equal to nj. Fill it out. Right, we can just say I equal to ni, j equal to nj. And this is turns. Right, we move turns. So basically we compute what the new position is going to be, right? And then we try to see how many we need to actually do within. And we fit out everything. So index will go through. So now the question now is, I know the steps, how many steps, right? So I have the start I and start j. So maybe in this case, steps. I think in this case I shall start with 0 and then don't do this, right? I start with 0 and then plus di times steps to give me the end, and then we try to see how many we need to do, and then we set up a new end, and then turns, and turns doesn't change, so when we do new things, okay. Let's see. Some analysis. Oh, out of reach. How is that possible? Let me think. Yeah, I feel like there's something wrong here. Let's say we get out of bound. Okay. Then let's say EI is out of bound. Okay, EI is out of bound. NI is out of bound. Okay, NJ is within. The NJ will be right. We'll find the right position, but if it's out of bound, then we shall not entertain it. Or should we? Well, the whole idea is if it's out of bound, right? If, like, say, EI was out of bound, and then we go in the other direction, then we shouldn't be recording anything, right? We shouldn't be recording anything. But if we go in this way, right, we are still out of bound. I is out of bound, but we go in inside, then we shall recording something. So it depends. Okay, so it depends on di and dj, right? So if and I, so we have I and we have ni, right? If ni is out of bound, it doesn't matter, right? If we are saying that if, so we need to know when not to fill, right? And not to fill is if ni is out of bound. No, not really. Ni is out of bound. Is I itself is out of bound. If I is out of bound, That's also not true. If I is out of bound and ni is out of bound, okay, so both are out of bound, but there are things in this range which is within bound. That's what we need to do. But if nothing is within bound, okay, so how do you check if they're within bound? Well, your check, because one of them will always be the same, right? If I is equal to ni, right? So we're moving horizontally, and they're out of bound, right? If I is equal to ni and then they're out of bound, that's basically a moot point. If j is equal to nj and they're out of bound, that's also a moot point. That, okay, we can do that. But if I is not equal to, okay, let's try this. So what I'm saying is, if I is equal to ni and I is smaller than 0, or I is larger or equal to rows, right? Or j is equal to nj and j is smaller than 0, or j is larger or equal to columns, right? These are the two conditions. These are the two conditions that we will skip. Otherwise, we'll do the following. So when do we do it? If I is not equal to ni, and or j is not equal to nj, within bound. Yeah. So it'll be like this. If I and it's within bound, and it's within bound, right? If everybody is within bound, I is equal to ni, right? And then they're within bound, then yeah, we can do it. Or j is equal to nj, and this is within bound. Right? If it's within bound, then we'll run it. If it's not, then it's just not. Okay, let's try this one more time. Still not right. Shoot. I see the problem. Yeah, I see the problem. No, it should be. Yeah, like you end up at this position, and then you compute. You know it's going down. So ij is here, right? And ij is here. Oh wait, hold a second. Are we double counting? I think we are double counting. Yep, I think we're double counting. Yeah, we're double counting. That's like one problem. I think there are multiple problems in this one. Double counting is one problem. I still am not convinced. So we're doing here, right? And then we're trying to do it again. Right, the start and then the end. And we have this, and we have and here. And we say I is equal to, that's false. J is within, so we need to try to fit. So we do one, but it's already been done before. Maybe we can fix this. So basically, every time we try to do, then we just need to compare to the previous one. If res index -1, okay, index is larger than 0, and not 0, not equal to ii. Yeah, because we need to know the previous cannot be the same, or res index -1 is not equal to jj. So only if we satisfy both, then we will put a new thing in. So okay, let's try this. A little bit check to avoid double counting. Ooh. The hell. Well, I don't know what happened, but what we can do is system.print out. I don't know. Maybe we'll print out something. If not, I'm gonna. It's not helping. All right, let's bring out the big gun. Yeah, we need a big gun for this. Big gun. This is the big gun. All right. Let's get the big gun out. It's always false. What? Oh, I see. My logic is bad. What? Dude, you gotta be kidding me. And man. All right, I have no idea. We need to really see. Okay, what is this? Rows, columns. Okay, so we got rows, column, r start, r end. Okay. Rows, columns, C start. My bad. C start. C. No, R start and C start. Function's name is Sparrow. Rows, columns, start, C start. Right, it's not right. What was the problem? Oh, that's fine. Okay, let's debug this baby. All right, so index is 0, right? So next, yes, step. So we have one step. Direction shall be 0 and 1. Okay, so ni shall be the same as I. Nj shall be 1, right? Nj is 1, and this is true. Yeah, because the I is the same, but they're within the range. So I'll do, we compute si's actual starting is 0, actual ending is 0. Because I doesn't change, and then actual j is 0, this should be 1. Yes. And then we say for this, for this, index is 0. So ij is 0. So we put 0, 0 in. Okay, index is 1. Now j, I have one more to go. Yes. Wait, hold a second. tj is 1, sj is 0, jj equal to 1. Huh? Wait, what? Okay, so now I is 0, jj is 0. We fit the first 0, 0. Okay. Index is 1. I is 0, j is 1. Ooh. And this is not equal to ii, and this is not equal to jj. This is false, this is true. How about this one? And this is false. Yeah, it should be or, right? It should be or, it's not and. This I think is an or. Okay, well, this is f8. 0, 0, done. 1, 1. Done, done. Huh? Oh, shoot. Oh, I see what happens here. I see what happens here. Okay. Yeah. All right. How do I run it? Yeah, cannot do it this way. All right, this one has to change. Yeah, it has to change. So basically, what I'm thinking is, okay, I have to change big time. Which is say, if I is equal to ni, okay, and I is larger equal to 0, and I is smaller than rows. Okay. Then we can compute the j's. Right? We have the sj, we have the nj, and we'll do this. Right, jj equal to this, blah blah blah, and all we need to check is not equal to I, not equal to jj, and then we do this. Then we copy the entire thing. Okay, copy the entire thing. Right, so we say if j not equal to nj, j is larger than, oh my god, it's so slow. It's way too slow, man. Okay, let's. Oh. Okay, so we say j larger j shows smaller equal to columns, right? And then we do this. We paste in here, do the i's, and then we say this is not jj, it should be this thing. Put back. Now this is true. Now this should not be, it should be J. And this is not equal to, wait, hold a second. This is II, okay? And this shall be J. How about that? Okay, we'll take a look. I'll run it first. Okay, this one looks good. Let's use all the template. Right, the second one is not correct. We'll figure it out. All right, let's see. Where does it go wrong? My. So we get 1 4 1 5 1 4 1 5 2 5 2 4 2 3 1 3 0 3 0 4 0 5. When we get out 0 6. What in the world? 0 6. Okay, yeah, this is not right. Zero 6. Why would it go 0 6? It doesn't make any sense. Right, it's getting out of bound because this is 0 1 2 3 4 5, right? It only has 5, and this is this case, right? J star J is correct. Could start with 3, right? And now we go to 4, then we go to 5, which mean and then this is not equal, so EJ is wrong. How is EJ computed? EJ computed is minimum of this. Then how is it impossible? Okay, let's see if we can get it out earlier. Let's just use this 5 6 1 4. Okay, 5 6 1 4. Yeah, that's all right. So steps 1. So we go 1. 2 basically, get out. Okay. I is 1, J is 5, right? So we end up I is 1, J is 5, which is correct. The next one, steps 1. I think this one is still correct. So our end is I is 2 and J is 5. So 0 1 2, J is 5. Okay. And next one is also correct. A couple. I is 2, J is 3. 0 1 2, 0 1 2 3. Yeah. So next one and should be I is 0, J is 3. Okay, I is 0, J is 3. Here is the interesting part. Next, the step shall be 1 2 3, right? The step shall be 3. Okay, Step 3, di is 0, dj is 1. And I is 0, and j will be 6, right? And then this is I is equal, and it's within a bound. Okay, so we'll go in, start j. Okay, so the j currently is, what's j currently? J currently is 3, right? Column is 6. So sj is 3. And j, that's the problem. And j. Shouldn't that be 5? Yes, nj is 5. Right? Nj is 5. Nj is 5. But my result, nj is 5. No, I think this one's right. It's when this is done. Yeah, what I did is this. Are we supposed to not handle this? Well, but j is the same, but it's out of bound. Right? I is not. J is also. Okay, let's finish this. Right? If we check the result, we have 030,405. That's correct. And is 06. Okay, that's perfect. Go back up. Don't do it. So now j is 6. I is 0. So now I is going to be 3 because I have to go down, right? 0, 1, 2, 3. I is correct. Now the problem is j. Right? And j will be 6. That is fine. Right? J is 6, and j is 6. This is false. Oh, typo. Mr. Typo. Damn. Not the first time we have typos like this. I actually have more typos. This should be J. Right? No, this is I. My bad. This is I. So we have one typo, which is here. Column is J. Man, it's well over 1 hour. Not one of those difficult problems, but Lord, it's I'm trying to make it fast, so it's kind of complicated. All right, this one is 885. Not a complex problem, but took a while to get all the logic in place. Mainly because I refuse to just, go through every single one. I just want to make it a bit faster. Okay, now here's the interesting part, right? Here's the interesting part because what I'm trying to do is, that's actually a good idea. I'm going to run a bunch of tests. I think I have 4 and 4. 1, 2, 3, 4. I think that's the last one, right? Yeah. But we can also handle the last one. Last one shall be 4 and 5. Okay. Let's see if this one handles it. Okay, I think it handles it pretty well. Yeah. That's alright. I wonder if there's any solution with easier logic. Simulation, of course you can do simulation. Oh. Huh. I think it's just complete simulation, right? Which is append. Yeah, look, it basically goes through every single one. So that's not what I want. I want it to be, it's not on squared. Dude, it's just, it's rows times. It's rows times column. So my complexity is faster than this. Yeah, it's not O(n) squared. It's just OMN. That's what it is. But to get to a better complexity, yeah, the problem gets a little more complex, and it took longer. All right, that will be it for today. We have to use a big gun today. That's fine. All right, see you guys tomorrow. Adios.